G'day viewers, this episode is a call to arms. We are seeking volunteers to assist us in our Spectral Signature Project, that is, the direct detection and observation of black holes. What skills in particular are we looking for? Well, some sort of scientific background would be great, particularly in astrophysics, cosmology, mathematics, radio astronomy, signals analysis or software development. Students are very welcome, and participation in our Spectral Signature Project incorporating student assignments may also be considered. The direct detection and observation of black holes would be a landmark achievement. We hope to execute a rigorous research regime, then publish a research article based upon the results. Of course, all participants will have an equal share claim to full recognition. Please reach out to me via the Gmail address appearing on screen. From episode 6, we know how the quantum vacuum and zero-point field may be mathematically described via Fourier harmonics. Utilising this mathematical description, we may postulate a physical interpretation of spacetime. This is precisely the same thing that general relativity does. That is, the mathematical model drives general relativity's physical interpretation of spacetime. Well, what's good enough for Einstein is good enough for us. Don't forget, the real value of general relativity isn't the theory, it's the mathematics underpinning the theory. Take the mathematics away from general relativity and you're not left with much. In fact, to demonstrate why it's the mathematics that is the useful part and not the theory, all we have to do is look for the application of the same mathematical techniques in engineering, such as stress and strain analysis. Tensor mathematics exists everywhere in various engineering disciplines, so we have clear evidence that the real value of general relativity lies in the mathematics underpinning it, not in the theory itself. We propose the following physical interpretation of our mathematical model. Number 1. All matter radiates conjugate photon pairs. Each conjugate photon pair constitutes a graviton. Number 2. Conjugate photon pairs are absorbed by the quantum vacuum. The quantum vacuum is the space-time manifold. They are the same thing. Number 3. Conjugate photon pair absorption into the quantum vacuum is not always perfect. That is, it is not always 100% efficient. Absorption of conjugate photon pairs into the quantum vacuum is a process, not an event. Hence, no process can be 100% efficient without violating the laws of thermodynamics. Number 4. Occasionally, one photon is absorbed by the quantum vacuum, whilst its conjugate partner evades absorption and propagates in the conventional manner. This is the photon we are looking for. This is the photon we want to detect. Please note that the 100% process efficiency we have discussed would require an infinite number of processes to occur for an infinite period of time, and we would need to be able to measure all of this to an infinite number of decimal places. Failing any of these requirements means that 100% process efficiency cannot be confirmed, is impossible to achieve, and consequently, the laws of thermodynamics have been preserved. So then, what is our high-level project strategy? What might our approach to this project look like? Number 1, recruit the appropriate team. Number 2, mind map project requirements. Number 3, mind map the solution. Number 4, identify and access the appropriate astrophysical databases. Number 5, develop custom software, if required. Number 6, test and validate the solution. The next couple of slides you'll see are direct excerpts from episode 6, which was recorded utilising a synthesised voice. We understand that some viewers may not enjoy listening to a synthesised voice, but please be tolerant because it provides important background information. Okay, let's get into it.
In this illustration, we see the zero-point field modeled as a randomized spectrum of real photons. This is the effervescent baseline of the quantum vacuum driving the Casimir effect. But where does the energy for these wavefunctions come from? If the energy for these wavefunctions existed at the level of the zero-point field constantly, then all the energy within the zero-point field would be released in one catastrophic event. Therefore, a layer of reality must exist beneath the zero-point field where the energy for these wavefunctions must be stored. This is why we describe the zero-point field as a dark reservoir of quantum potential energy. In order for virtual photons to pop into existence, they must have been stored in some inaccessible layer of reality, as potential energy. Due to the storage layer for this quantum potential energy being physically inaccessible, we may imbue it with any structural format we wish. All logical formats are equally valid as they cannot be directly experimentally confirmed. Please do not confuse or associate this statement with the Casimir effect, which is experimentally observable. The Casimir effect occurs in the real world, but the dark reservoir of quantum potential energy fueling the Casimir effect is physically inaccessible. Therefore, it logically follows that any structural format applied to describe this dark reservoir of quantum potential energy should be efficient, in order to be consistent with all other natural phenomena. Hence, a very efficient way of storing quantum potential energy, mathematically speaking, is in accordance with a Fourier distribution. In the bottom left-hand corner of this illustration, we see the quantum potential energy associated with the zero-point field. The zero-point field is the physical manifestation of the quantum potential energy released into the physical universe when the quantum vacuum is in its ground state. We manifestly observe this process in the Casimir effect. The illustration depicts the amplitude and frequency spectra associated with the available quantum potential energy, formatted in accordance with a Fourier distribution. As described by the unit harmonic operator in episode 2, each wave function denotes a population of virtual photons and exists in conjugate pairs, as indicated and required for net zero gain. Hence the term, zero point. These wave functions mean that at any instant in time, populations of virtual photons pop into existence, but so do an equivalent population of virtual photons, 180 degrees out of phase. Consequently, no electromagnetic radiation is ever experimentally observed, mysteriously appearing from nowhere. So how do we interpret these curves? That's a good question, I'm glad you asked. The amplitude of each wave function denotes the probability of a population of photons popping into existence. As you can see, the probability of emergence into reality is significantly greater at lower frequencies than it is at higher frequencies. That is, the higher up the frequency spectrum we look, the lower the probability of virtual photons popping into existence. And as we have already established, for perfectly flat space-time geometry, the harmonic cutoff frequency tends to infinity. This also means that its probability amplitude tends to zero. In other words, it is impossible for photons of infinite frequency to exist in the physical universe. Hence, the universe cannot catastrophically collapse. When we add matter to the zero-point field, a major change occurs. The quantum vacuum becomes polarized by the presence of matter and compresses the frequency range of the zero-point field. The lower spectral frequency limit is upshifted from 0 Hz, and the upper spectral limit is downshifted from infinity. Both alternate spectral limits are mass-energy dependent. However, the structural format of the Fourier distribution is preserved. In other words, the mathematical description doesn't change, the Fourier distribution is preserved, but its lower and upper frequency limits have been modified, due to the addition of matter. We call this polarized form of the quantum vacuum, the polarizable vacuum. So how does all of this lead to the topic of gravitons? Well, if we consider any mass to be represented by a point particle, we are in fact insisting that all of its mass energy is contained in the quantum vacuum field surrounding it. Hence, if the quantum vacuum surrounding any mass can be described by a Fourier distribution, which is fully quantized, then it logically follows that a conjugate photon population pair must define the graviton. And an important question now is, what are the gravitons interacting with? How is space-time curvature generated? The answer to this will be discussed in detail on the following slide, but for now, we'll say that matter is analogous to an energy source, whilst the zero-point field is analogous to an energy sink. Let's take a closer look. So far, we have established a link between the zero-point field and the layer of inaccessible reality beneath it, termed the dark reservoir of quantum potential energy. However, if the dark reservoir of quantum potential energy feeds the zero-point field, what is feeding energy to the dark reservoir? To answer this question, we first propose that one pair of conjugate photons constitutes one graviton, and that baryonic matter evaporates via graviton radiation. This mechanism feeds the dark reservoir of quantum potential energy. In other words, baryonic matter radiates populations of gravitons which are absorbed by the dark reservoir of quantum potential energy, via the zero-point field interface. General relativity interprets this absorption as space-time curvature. Hence, the mechanism we have described is isomorphic to general relativity. However, as one might expect, the store of gravitons within matter is finite. This means that all matter possesses a minimum gravitational lifetime. But don't worry, we'll cover this in a later slide. The important takeaways from this illustration are: 1. All matter acts as an energy source. 2. All matter evaporates via graviton radiation. 3. The gravitons radiated by matter are absorbed by the dark reservoir of quantum potential energy, via the zero-point field interface. This means that the dark reservoir of quantum potential energy acts as an energy sink. 4. The zero-point field interface is a bidirectional information layer, allowing gravitons to enter the dark reservoir of quantum potential energy, but also acting as a pressure release valve which we perceive as the Casimir effect. To ensure that the dark reservoir of quantum potential energy inflates very gradually, the zero-point field releases energy back into the physical universe to drive the experimentally observed accelerated cosmological expansion. Now that we have these fundamental concepts in place, we're in a position to start doing some calculations. So, let's move forward.
From episode 6, we know how the quantum vacuum and zero-point field may be mathematically described via Fourier harmonics. Utilising this mathematical description, we may postulate a physical interpretation of spacetime. This is precisely the same thing that general relativity does. That is, the mathematical model drives general relativity's physical interpretation of spacetime. Well, what's good enough for Einstein is good enough for us. Thus, we propose the following physical interpretation of our mathematical model. Number 1. All matter radiates conjugate photon pairs. Each conjugate photon pair constitutes a graviton. Number 2. Conjugate photon pairs are absorbed by the quantum vacuum. The quantum vacuum is the spacetime manifold. Number 3. Conjugate photon pair absorption into the quantum vacuum is not always perfect. That is, it is not always 100% efficient. Absorption of conjugate photon pairs into the quantum vacuum is a process, not an event. Hence, no process can be 100% efficient without violating the laws of thermodynamics. Number 4. Occasionally, one photon is absorbed by the quantum vacuum, whilst its conjugate partner evades absorption and propagates in the conventional manner. This is the photon we are looking for. This is the photon we want to detect. Number 5. Detecting these photons is analogous to identifying 2 to 330 specific electrons from the cosmic background noise. As you can imagine, filtering out all cosmic background noise so that you can identify 2 to 330 specific electrons which have your name written on them is going to be an extremely difficult task. Of course, these electrons are only an analogy, but it clearly communicates the difficulty of the task. Let's now compile a project strategy. Firstly, in case you were wondering about utilising 2019 particle data group information instead of 2024 information, you can see from the results on the screen that the deviation from the previous slide is trivial. Particle data group 2024 information yields an upper limit of specific electrons equaling 328 instead of 330. For the purposes of conceptualization, 328 equals 330. Okay, that's enough distraction. Let's talk about a high-level project strategy. So then, what might our approach to this project look like? Number 1, recruit the appropriate team. Number 2, mind map project requirements. Number 3, mind map the solution. Number 4, identify and access the appropriate astrophysical databases. Number 5, develop custom software, if required. Number 6, test and validate the solution. Allow me to repeat an important point made on the previous slide. Conjugate photon pair absorption into the quantum vacuum is not always perfect. That is, it is not always 100% efficient. Absorption of conjugate photon pairs into the quantum vacuum is a process, not an event. Hence, no process can be 100% efficient without violating the laws of thermodynamics. Well, I hope that I've been able to convince you to jump aboard the Spectral Signature Project, that is, the direct detection and observation of black holes. Please reach out to me via the Gmail address appearing at the start of the video presentation.